Hello everyone, welcome to the first video for the final section that we will be covering for the quarter, the final bit of new information we need to cover. Kind of crazy that we're made it this far already, but here we are. Okay, so this section is on something called antiderivatives, and I'll get to what that is in a minute. But first, let's play a little game. And I like to call this game Name That Function. And if we were in a classroom, I would get really excited and put on my best game show host voice and go over this. But here's the idea, is we have a set of derivatives here. So we've given a set of functions that we know what the derivatives are. And we have to figure out what were the original functions. Okay? And we have to use a little bit of sleuthing here, although I think for some of these, y'all will be able to recognize them. So the first one, 2x. So we see that that is polynomial looking thing there. So we have to figure out what was f of x, the original function we started with. And again, it's a polynomial looking thing, which means that maybe we used the power rule here, which would mean that this looks like it could be maybe what was in the exponent. So perhaps we think that the function here, the original function would have been x squared. And if we double check that, we take the derivative of x squared, that does in fact give us 2x. Okay, so that's what we're doing here, kind of working backwards. All right, next one. G prime of x equals negative sine of x. Now that one looks familiar, right? We actually know a function whose derivative is negative sine of x. And that would mean that in this case, oops, I'm doing blue, g of x would be cosine of x, right? Because we know the derivative of cosine is negative sine. All right, cruising right along here. Now we have h prime of x equals 1 over x. Now if you recall, 1 over x is a derivative or a special derivative of something. And what is that? All right, we recognize that as the derivative of ln of x. So recall that the derivative of ln of x is 1 over x. Now, on these last two, notice that we've kind of relied on knowledge of specific derivatives of particular functions, right? So the first one we had to use a derivative of one of our trig functions, and this one we had to remember that ln of x has the special derivative that's 1 over x. So that's some of what you do on these ones. All right, for v prime of t equals 16 t cubed. Well, again, we see that there is a polynomial there, which makes us think that perhaps the power rule was used here to take the derivative. Okay. Also note or remember that when we use the power rule, we subtract 1 from the exponent. But since we're going backwards here, we'll actually probably want to add 1 to that exponent. So it would probably be t to the 4th. And if that's true, then what would the coefficient need to be to give us this 16? Right, that would be a 4. So we'd have 4t to the 4th is our derivative there. And if we check it, 4t to the 4th, take the derivative there, we do get 16t cubed. All right, what about this last one? Well, we have 2s times e to the s squared, which looks like maybe we'd have to undo some product rule or something, which looks kind of nasty. But also notice that this 2s here is the derivative of s squared. So that makes me think that maybe there was some chain rule action going on there, which also leads me to believe that the derivative, or the antiderivative here, the original function was e to the s squared. Now let's think about this, if that works. We know we're taking the derivative of e to the power of something. It just gives you the same thing, right? If we're going to take the derivative, so we have e to the s squared, but then by the chain rule, we have to take the derivative of the exponent, which would give us 2s. Okay, and that's our original function back here. So that tells us that this answer here is correct. Okay. All right, and if you want to go back through back in the video and rewatch this portion to recall what I did, that might be a good idea. But I'm going to move forward here and talk about, again, antiderivatives. So what we just did for each of those functions, even though we were kind of doing backwards derivatives or going back from the derivatives, what we really found were the antiderivatives. So a function, and notice here they use capital F, is called an antiderivative of a function f on an interval I if f prime of x equals f of x for all x and I. So kind of an example of that. On the last page, we had f prime of x was 2x. And then sometimes instead of writing f prime, or if we're just given that the derivative is f of x, we'll write the antiderivative as capital F of x of 2x. And then something I forgot to mention on the previous slide is, or to get you to think about, is 2x, sorry, and that is completely wrong. This should be x squared, my bad, sorry about that. Is x squared the only thing whose derivative would give us 2x? Well, what if I did this? What if I made this function x squared plus 7? Is the derivative of that still 2x? I think it is, right? Because we could take the derivative of the x squared, that'll give us a 2x. Derivative of the 7 just gives us 0. So that'll work. But is that the only one? Well, no, we could also do plus 13, right? X squared plus 13, take the derivative there, still gives us 2x. What if I did x squared minus 1,000? Does that still give us 2x when we take the derivative? I believe it does. What if we do x squared minus pi and take the derivative? Does that still give us 2x? It does. So it looks like then there are an infinite number of answers for what the antiderivative could be here. So to deal with that, what we do is instead of writing all the possibilities with all the numbers that could ever be added there, we put this plus c, and we're taking a general antiderivative, okay? And as it says below, what that represents, that c is an arbitrary constant, because without more information, we don't know exactly what the constant was, or if there was a constant on the original function before we took the derivative. So we put the plus c there to represent that. So there's this theorem here that says that if capital F is an antiderivative of f on the interval I, then the most general antiderivative of f on I is f of x plus c. So again, we put that plus c there to represent the possibility that there could be a constant on the function. Okay. All right, one more thing. Just some kind of general formulas for antiderivatives. And none of these are really anything new, it's just kind of some reminders. So first of all, as you can imagine, when we take derivatives, we have the constant multiple rule, where if we have a constant times a function, the derivative is the constant times that derivative of that function. Well, same thing with antiderivatives. So we have a constant times a function, the antiderivative is a constant times the antiderivative. We have a bunch of functions being added or subtracted. We can take all of their antiderivatives individually. And then this rule here is one that we can kind of use when you are taking an antiderivative of a power function. So we know we have our power rule to find our derivatives of power functions, where we move the exponent down and subtract 1. Well, the opposite of that is to add 1 to the exponent, but then also divide by that or multiply by 1 over that. And that's an example of that. If you're taking the antiderivative of x cubed, well, notice if I add 1 to the exponent, that gives me 4. And if I multiply that by 1/4, you can check that if you take the derivative of that, you get x cubed. Okay. Another important thing I want to point out here is when we take the antiderivative of 1 over x. So when we did that on the first slide, Okay, we just wrote 1 over x, or excuse me, ln of x, because we know that's the derivative of that. But notice they put the absolute values here. And the reason for that is that in the domain of 1 over x, x can be either positive or negative numbers. But in the domain of the natural log, they can only have positive numbers. So that's why we have to put the absolute value here. So if we're talking about evaluating antiderivative of 1 over x at a particular point, we can still use absolute value signs. Okay. The rest of these hopefully make sense about the trig functions, and then they also have the inverse trig functions here. These ones in the bottom right there, you do not need to worry about. Those are what we call hyperbolic sine and cosine, and we do not cover that. Okay. All right, that's all I have for you now. Thank you for watching.